Hi. In this experiment, I'm investigating how different factors affect the magnetic field inside a coil that I made with my bare hands, as you can see. I'm changing the number of turns, the length, the current, and the type of wire that I'm using to see how these factors affect the magnetic field created by the coil. And I'm calculating the magnetic field with using Gauss measure, as you will see later in the video. Alright, so here's how we conducted the experiment in 6 steps. First, we formed our solenoids by tightly winding wire around a cylindrical object, which we later removed. Removing it made sure the magnetic field measurements wouldn't be affected by a different permeability. And secondly, we set up the circuit, connected a power supply across the solenoid, added a 100 ohms resistor in series to create the noticeable current, and hooked up the multimeter across the solenoid to measure the current. Third, once the multimeter gave a stable reading, we inserted the Gauss meter horizontally into the solenoid right at its midpoint, and recorded the magnetic field value in Gauss. Fourth, we calculated the expected magnetic field value using the formula from the theory section, since we already knew the solenoid and circuit parameters. Fifth, we repeated everything, but each time we changed at most one feature compared to the original setup, so we could see the effect of that change. And finally, in step 6, we gathered all the data. We used the two setups with no changes or controls, and compare it to the others by calculating the error percentages, which I will show later in the video, just like the theory section described. Here you can see all the data that I conducted and the features of the setups that I created for our experiment. Some quick notes about why we didn't stick to a single control setup and the unusual Gauss meter readings. Originally, the plan was to have just one control as the setup 1, but while building the solenoids, it became clear that making one with 15 centimeters length and 40 turns wasn't practical because the material kept stretching when I'm making it. So, we created an alternative control setup and cross-checked it with the original to ensure consistency, as seen in the data table. The new created setup is the setup 3. That's why both setup 1 and setup 3 served as controls. As for the Gauss meter, it gave readings about 10 times higher than expected for some values, even for identical setups. After discussing with Professor Saadet Karateke, he decided to focus on the ratios between setups, which stayed consistent with the theory, rather than the absolute values. As a result, only the relative changes were used in the final evaluation, as you will see later in the video. And now you can see all the comparisons that I made with the setups. For example, I made a comparison between setup 1 and 2 to see how current affected the magnetic field created on a solenoid by current. And a few comments about the enormous error we saw in the effect of length and the other sources of error. Like I mentioned earlier, the Gauss meter seemed to struggle with magnetic fields below 0.1 Gauss. It simply didn't register anything lower. Most of our calculated values were well under 0.1 Gauss, except for setups 1 and 2. So comparisons for other features stayed pretty consistent, but when we looked at the effect of length, setups 1 and 3 didn't match well because they were different in value ranges, which drove off the ratio. If we trust that setup 3's observed value should be around 0.04 Gauss, the percentage error drops to about 8.7%, which is a big improvement compared to the initial error. So the biggest source of error was likely to the Gauss matter itself. As for the other errors, they followed the expected patterns based on the changes we made. Most of them probably came from human errors, like small inconsistencies in the way we want solenoids by hand, because they were made by my bare hands, which will affect the turn density. Also, the solenoids weren't perfectly straight, they were a little curvy, which made it tricky to measure their lengths accurately. And finally, the Gauss meter didn't have enough digits to give precise measurements, which added to the uncertainty. And now, to conclude my video, it can be said that in this project we aim to investigate which features affect the magnetic field created by a current flowing through a solenoid. The theory suggested that the magnetic field should depend only on the current, the length, and the number of turns, not the type of wire. That formula can be found by applying the Ampere's law on a solenoid. We carried out the experiment in 6 steps, and because of some equipment difficulties, we used 2 control setups instead of one. The gas matter did cause a few problems, especially affecting the investigation on the length feature. But overall, the data we collected matched the theory really well, and the errors were relatively very low compared to the errors seen with the length. In the end, we can say that applying Ampere's law to a solenoid gives a very accurate understanding of how its magnetic field behaves.